Okay, welcome everybody to the May Institute for Environmental Futures seminar. A very warm welcome also to our audience who are joining us via our live stream on YouTube, so hello to you. I just have to say before we begin properly that we'll be recording and live streaming today, so just to make you all aware of that. And we'll be making this seminar available via YouTube as well if you want to catch up or watch it again. Apologies from the director of the Institute for Environmental Futures, Professor Heiko Belzer. He's in Rome today, so I'm chairing today in his place. My name's Emma Stockley, and I'm a PhD student at the School of Archaeology and Ancient History here at University of Leicester. And I'm absolutely thrilled that today we're welcoming a fellow archaeologist from the school who's going to present. We've got Dr Nichole Sheldrick. Unfortunately, Dr Ahmed Mahmoud is unable to join us, but I'll be introducing them both. So today's talk, monitoring threats to archaeological sites and landscapes in North Africa using Google Earth Engine. So Dr Nichole Sheldrick is senior researcher in digital archaeology for the Endangered Archaeology in the Middle East and North Africa project in the School of Archaeology and Ancient History. Her research focuses on the archaeology of North Africa, particularly rural landscapes during the Roman and late antique periods, and also on the development of rapid remote sensing and automatic change detection methodologies for the purpose of heritage documentation and the management and protection of heritage at risk. Dr Ahmed Mahmoud is a remote sensing geoscientist with a PhD in surveying, engineering and space geodesy from the University of Nottingham. His expertise focuses on the use of remote sensing, GIS and land surveying for Earth observation and environmental monitoring. Ahmed is currently working as research associate on the Endangered Archaeology in the Middle East and North Africa project, with primary responsibilities contributing to the development of the AMINA automated change detection ACD system to monitor and predict threats on archaeological sites, as well as the development of user interfaces on cloud computing services to be used by local antiquity services to support the management and preservation of heritage sites. So it's my great pleasure to welcome Nichole, who's going to present to us today. Thank you very much.
Hey, good afternoon, everyone. And thank you, Emma, for that very nice introduction. And thank you to Emma and Heiko and the Institute for Environmental Futures for asking myself and Ahmed to give you this presentation today. As Emma said, Ahmed unfortunately can't join us today due to some unforeseen circumstances, but he does send his apologies. So today I'm going to present some recent work on automated change detection methodologies for the purposes of monitoring threats and damage to archaeological sites in North Africa, which Ahmed and I have been doing for the Endangered Archaeology in the Middle East and North Africa project, or EAMINA for short. I just want to start by providing a very quick bit of context about our project and about how we use remote sensing for heritage monitoring and protection for those who are not familiar, as I know not everyone in the audience here are archaeologists. So the AMINA project was founded in 2015, and the catalyst for the project was a recognition of the kind of growing number of threats that are facing heritage sites around the globe, but particularly in the MENA region. This, of course, includes the well-publicized, extreme, and intentional damage that was done by terrorists to archaeological sites in the Middle East and other regions. On the screen are, of course, just a couple of examples that I'm sure many of you will remember of the terrible damage done to Palmyra in Syria and Nimrud in Iraq. It also includes large-scale organized looting, which feeds into the illegal antiquities trade. On the screen, we can see the devastation that this type of looting can cause, with thousands of illegal looting pits dug at the Roman site of Apamea in Syria in just under a year between 2011 and 2012. So for many people, when we talk about heritage at risk, these are often the kinds of things that come to mind, and these are without question very important issues. But actually, these are not necessarily the biggest threats that are facing archaeology today. What we've found on the AMINA project is that one of the biggest threats to archaeological sites is actually agricultural expansion. Sites in rural areas are often already situated in agricultural land, and this can result in long-term continuous damage to sites. As you can see in the example on the left, we have the remains of a Roman period building, And you can see that the top half has already been entirely destroyed for the farms that you see there. And probably there's like the stone field walls that you can see have been built out of the stone that was built, that was used in the original Roman building. And then in addition, you can see the bottom half, the kind of surviving part of the building, is being subjected to plowing all around it, which over time will continue to erode and destroy it further. In addition, thanks to new technology like center pivot irrigation, agricultural land is being pushed into regions where it's never been possible before. And this is having a big impact on archaeological sites like the Desert Kite that you can see on the right, which is a kind of ancient hunting structure, probably at least 2,000 to 3,000 years old. So until the last few decades, sites like these have been protected by their remote locations deep in the desert, but they are being encroached upon more and more. Oh, my goodness, sorry. Something happened on my screen. Sorry. Okay, similarly, growing populations mean that towns and cities are expanding at an unprecedented rate, affecting the heritage sites within and around them. And so you can see some more examples on the screen showing how a modern cemetery on the left and a settlement on the right are expanding right over the top of ancient sites. Another common problem is things like mining and natural resource prospection. On the left, you can see the remains of an ancient gold mining site. People have been mining gold in the same location for literally thousands of years, from the dynastic Egyptian period onwards. But we can see that how in the matter of a decade, the ancient gold mining site has been completely overwhelmed by the modern one on the right. And it's clear that the techniques now being used are rather more destructive, both to the archaeological site, but also the landscape surrounding it. Finally, another growing concern is the effect that climate change is having on archaeological sites. Rising sea levels are having a serious impact on coastal sites, like we can see on the left at the site of Sabratha, which is a Roman city on the coast of Libya. And then on the other side of the coin, increasing rates of desertification in many areas is also contributing to the degradation of archaeological sites, like we can see with the tower on the right being swallowed up by shifting sand dunes. And so all of this is just to give you a kind of sense of the variety of threats that are facing heritage in the MENA region. And it's within this context that the Endangered Archaeology Project was established. Now, the project is a collaboration between 3 UK universities, Leicester, Oxford, and Durham, with postdocs based at each institution. And we are generously funded by a philanthropic organization called Arcadia, who support work to preserve endangered cultural and natural resources, as well as promoting open access to knowledge. So the MENA project has a few main aims, as you can see on the screen. The first of these is to document archaeological sites across the Middle East and North Africa as a baseline inventory for heritage protection. And second, specifically to record and track over time the condition of these heritage sites and any threats that they face. And this is to help us understand larger trends and patterns in damage to archaeological sites, and ultimately to help us learn how we can mitigate these issues in the future. We do conduct field work and collaborate with in-country partners who are doing so, and this remains an essential aspect of our work. But actually, our main source of information comes from remote sensing techniques. And so a third main focus of the project is the development and improvement of remote sensing methodologies and workflows for heritage recording, and also to see how we can improve and deploy these methods for use as tools for rapid recording and assessment. And of course, this is the main thing that I'm going to talk about today in terms of our work with Google Earth Engine. But last, but definitely not least, I do just want to mention the fourth main focus of our work, which is to share the data that we collect and the methodologies that we develop with partners and stakeholders in the Middle East and North Africa region. Since 2017, we've run nearly 30 training workshops in 10 different countries to train heritage professionals in our data collection and remote sensing methodologies. And this work was largely funded by the British Council's Cultural Protection Fund. So with those goals in mind, we've developed an online database using the open source ARCHES software. I'm not actually going to talk specifically about the database or ARCHES today, but the database is free to register for researchers. And if you're interested, you can sign up at the address at the bottom of the screen. And of course, I am very happy to answer any questions about it if people are interested in this aspect of our work. But as you can see on the map, what this is showing is the distribution of sites that have been recorded in our database. And you can see that we currently have just over 190,000 heritage sites recorded in the database, spread over a massive area from Mauritania to Iran. And this number continues to grow. And so dealing with this vast area and this kind of huge numbers of sites, this is one of the reasons why remote sensing has become so important to archaeologists and heritage professionals. In the last 15 to 20 years, the availability of high-resolution imagery via platforms like Google Earth has pretty much completely transformed the way that a lot of people are doing archaeology. As I'm sure most of you will be aware, as long as you have a computer and internet access, Google Earth is free, it's easy to learn and to teach people how to use. It doesn't require specialist skills or expensive software, just a little bit of guidance and practice. And so for these reasons, the AMINA project has really emphasized the use of open access platforms like Google Earth in our core methodologies. Many archaeologists are not formally trained in advanced remote sensing methodologies. And so platforms like Google Earth offer a really easy way in for people to understand how and why remote sensing in general and satellite imagery is now such an important tool. Now, the main thing that we use it for is basic visual image interpretation. And this provides a really rapid and low-risk means of collecting data from anywhere in the world. And it allows for simple and rapid site monitoring, as you can make repeated remote visits to sites. This is globally applicable, but it is particularly effective in the Middle East and North Africa regions due to low levels of vegetation and sparser modern settlement and less cloud cover. As you can see in the examples on the screen, how clearly some of these sites show up. However, as already mentioned, population growth and agricultural expansion mean that this situation is rapidly changing. Now, just to illustrate very quickly with one example how remote sensing survey has really been able to change the way we do archaeological survey. In Libya, for example, since the revolution in 2011 and until only very recently, it's been effectively impossible for foreign missions to work in the country. And the situation continues to be difficult and not always safe for our local Libyan colleagues. So remote sensing has offered a way for both Libyan and foreign archaeologists to continue to conduct archaeological surveys and monitor sites which are under threat. So for our methodology, the AMINA project has divided the region into these grid squares that you can see on the screen, each of which cover a quarter of a degree longitude and latitude, which equals about 25 by 27 kilometers in size to conduct satellite imagery surveys. Now, if we just zoom into the square highlighted in red, just up here in the northwest of the country, what you can see here in yellow is the distribution of published sites in this particular area, of which there are around 100. These sites were largely recorded in the 1980s by a survey called the UNESCO Libyan Valleys Archaeological Survey, and they recorded, among other things, these amazing fortified farm buildings, which date back to the late antique, late Roman period from the kind of the 3rd to 6th centuries AD. Now, a couple of years ago, I then was interested in this region, and I undertook a remote sensing survey over the same area to see whether there were more sites. And these were the results. In red, increasing the number of known archaeological sites in just this single square from just over 100 to over 1,000. This only took me a couple of days doing a very simple visual image interpretation survey in Google Earth. This included previously unrecorded settlement sites like the ones pictured here, and thousands of wadi walls and extensive field systems, which are evidence of agriculture and sophisticated irrigation practices taking place in the region nearly 2,000 years ago, in an area where agriculture is now not really supported today. Now, it's really important to emphasize that this is in no way a reflection on the methodologies or quality of that previous survey or any other surveys that take place on the ground. What this just demonstrates is the advantages that satellite imagery survey does offer archaeologists, which is the speed of survey and ease of access to remote places. Another really important and useful thing that remote sensing offers archaeologists, particularly in Google Earth, is the time slider function. That is the ability to track landscape change and the condition of archaeological sites over time. So in another example, we can take this prehistoric cemetery in northern Oman, which was recorded by a member of our team in Durham. So here, each of the little black dots that you can see. They're very small. I don't know if you can kind of make them out, but each of these is an individual cairn tomb. So this is a very extensive cemetery. And here, so you can see the locations of each individual tomb marked to make it a little bit easier to see. And you can already see up here that there is some construction happening in the area already. But if we just start moving forward through time, we can see the huge impact that the construction of this interchange has obviously had on the cemetery, and how many tombs are likely now completely destroyed. This is, well, it's very sad, honestly, but having this information is incredibly important and really useful information for heritage professionals. And the thing is, this would have been really, really difficult for people to collect on the ground. And so this just gives us a much easier way to see the effects of this construction work after the fact. We also make use of historic aerial photography and satellite imagery, like the declassified Corona spy satellite imagery, which can give us an even longer view through time. So here we can actually see how the old town of Sukma in southern Libya has changed over nearly 100 years. On the left, we have a historic aerial photograph that was taken in the 1930s. And then in the middle, we have this satellite image, Corona satellite image from 1972. And then we can see that by 2013, you still have this kind of ghost outline of where the old town used to be, but of course it's now completely destroyed. So those are the kinds of ways that we were able to make use of basic visual image interpretation, but increasingly archaeologists are also making use of other forms of imagery analysis and processing. So now in this example, we have a false color Landsat composites to show how agriculture has expanded in the Jufra oases in central Libya over time. So this first image we can see is from 1987, showing the extent of agriculture in red. And we can see the expansion already in 2001. And then in 2016, we can just see how much more area is now being devoted to agriculture. I also haven't produced a more recent one yet, but we can probably expect that by 2023, it's probably expanded even further by now. Now, obviously, this kind of analysis, these kinds of satellite imagery processing and analyses are being done by a lot of remote sensing scientists in many fields for many reasons, perhaps by some of the people in this room or online. But obviously what we do in archaeology is then combine these data with what we know about the location of and nature of archaeological sites. So if we zoom into just one of these oases, we can see much more clearly how this agricultural expansion is affecting archaeological sites. Highlighted in blue on the images are the archaeological sites. In particular, the light blue lines towards the bottom of the images are the roots of ancient underground irrigation canals, sometimes called kanats or fogaras. And you can see on the right just a close-up image of one. So it's this kind of series of mounds that represent shafts that lead to the underground canal. And you can see how they're being overwhelmed by the expansion of these agricultural fields. So all of these methods, they are very effective, and they're already being used by many archaeologists around the world to identify sites and document damage and threats. But one of the most important things that is necessary for effective heritage protection is not just documentation of these issues, but continued monitoring over time. You have to go back and check on sites because some of the damage is happening so rapidly. So if we look at our map again, and the scale of the area and the number of sites that we're dealing with, as you can probably imagine, even using remote sensing techniques, this is a mammoth task, especially given the limited resources which are typically available to archaeologists. So this is why our project, just like many others, is obviously now working on developing automated systems so that we can speed up these processes and help heritage professionals make rapid, informed decisions about where to target our limited resources. So for these purposes, as the title of my talk indicated, our project has primarily been using Google Earth Engine. Now, some of you may already be familiar with this platform, but for anyone who is not, basically Google Earth Engine is a free online platform which allows users to access Google's enormous catalog of satellite imagery and spatial data sets. And then what you can do is write and run your own customized analyses over these data in the cloud using Google's high processing servers, so that analyses that might take hours or even days to kind of run on your average laptop can be done in a fraction of the time. Now, when we talk about monitoring archaeological sites, which I just mentioned, we've sort of outlined four main questions that need to be answered when monitoring archaeological sites. First, we want to know, has a change actually occurred at a site or not? Two, if a change has occurred, what type of change has happened? Three, when did this change occur? And four, is the identified change or threat ongoing? Now, to answer the first of these three questions, or of four questions, the AMINA project already has an established automated workflow. This version was actually originally developed by a previous member of the AMINA team, Dr. Louise Rain, and it was published in the paper that you can see on the screen in 2020. Now, very briefly, this script works by processing and subtracting the values from two Sentinel-2 composite images to create a map of where changes have been identified. The locations of known archaeological sites with user-defined buffer zones are then incorporated into the analysis, and in any instances where the areas of change fall within the buffer zones of archaeological sites are highlighted for the user. So as you can see in these two examples here, in the blue in the upper right, those are the areas where the algorithm has detected a change between two images, and then we have the buffer zone, which is set at 100-meter radius in this case, of the archaeological sites. And you can see that the changes intersect the boundaries of the archaeological site, and thus these are highlighted in a list to the user. So basically what this does is then it indicates which sites have changed within their buffer zones, and then it allows us to then go validate the sites where the change has been identified using high-resolution satellite imagery, or if possible, going into the field. And that's what you can see on the bottom images. So what's been detected in these instances here is some bulldozing, and you can see the effects of it on the ground when a colleague was able to go out and take these photos of these same sites for us. Now, here's just another example of the kinds of results it produces. So on the left, you can see the Sentinel-2 composite that is produced by the algorithm in Google Earth Engine. And then in white, the area where it detected change. So those are all the pixels where it said there's been a change between the two images. And you can see that it's highlighted the two sites in red that it identified. So when we validate this with high resolution imagery, we can see that what the detection has picked up on the right is this large area of runoff, this kind of green, huge puddle, which is flooding an abandoned medieval site. So the advantages of this version of the AMINA change detection system is that it's fast, it's very simple to apply, and it's easy to adapt in various study areas, as it only relies on analyzing two images to detect changes. However, the disadvantage is that it only really answers the first question on our list here, not the other three. And so what we've now been working on is a method which will help us to answer the other three questions. Primarily, what type of change has been detected, which we do by running a supervised classification of the images, but also getting a better sense of exactly when the identified changes have occurred, and if the changes are still ongoing by incorporating time series analysis. And I do just want to highlight here that the methods from this point onwards of this new change detection methodology that we are developing are very much the work of my colleague Ahmed, who again, unfortunately couldn't be here today, but I just want to highlight that this is very much his work and what he's been doing for us on the project. So these are the basics of the new version that we're developing. For the moment, we've continued to work with Sentinel-2 imagery. If you're not aware, the resolution of Sentinel-2 imagery is 10 meters per pixel. So this does mean that there are limitations on the detail that these scripts can identify. For example, small disturbances like a single small looting pit will likely not be picked up. However, the frequency of the images captured 2 to 3 times a month in any given area, and the fact that it's open source really do make it ideal for our work. And it still works great for detecting larger landscape change, such as urban and agricultural expansion and infrastructure projects. So this is the kind of thing that we're focusing on. We're also exploring the possibility of adapting the methods for higher resolution imagery, which is usually not free, but it's also obviously useful if you can get your hands on it. Currently, we're looking at planet imagery, which is a 3-meter resolution, and ultimately want to do some tests to compare the results, but we're still in the early stages of that. Now, so I won't go into every detail of this, but essentially, this version of our methodology relies on using a machine learning model, random forest, to apply a supervised classification on multiple images and then performs a time series analysis. This version is a bit more intensive than the previous kind of binary version, as it requires the user to input training and validation data sets. And we've used a combination of high resolution archived imagery and fieldwork to obtain our validation and training data sets. And then, as you would expect, we filter the data based on area and dates of interest, sorry. Now, it provides various outputs to demonstrate the changes in the study area, such as classification and change maps, time series data, and statistics. Now, we do have a working version of this, which I'm going to show you some examples from, but we are still in the middle of undertaking the testing and validation of the results. And there are still some issues that we're trying to iron out, but I'll come back to a couple of those later. So let's take a very brief look at a couple of case studies so I can demonstrate the kind of variety of results that we're able to get from these analyses. Now, we've been working on 2 case studies in North Africa. And the first one we're going to have a look at is centers on the town of Beni Walid, which is in northwestern Libya. So here you can see the specific study area that we're looking at outlined in the red box, with a distribution of known archaeological sites within that area shown in the blue dots. Now, this area has been pretty much continuously occupied since at least the first millennium BC and probably earlier. And you can see a couple of examples of some of the most common types of sites that are visible and found within and around the city, from Roman and late antique farm sites to medieval villages. But the biggest threat in this area is urban and agricultural expansion. And so you can see, comparing these 2 maps, how much the city has expanded in a little over 50 years. So on the left, we have a corona image, and you can see hardly any buildings in this part of the wadi, but you can see on the right how the city has just exploded from the edges and continues to expand outwards. And you can see how clearly it's overwhelmed all the archaeological sites, this time noted in red, along the riverbanks. So we decided to investigate a 4-year period between January 2019 and January 2023 to see what kinds of changes we could detect during this time. And the first thing that our ACD script does is to apply a land cover classification to all the Sentinel-2 images that it can find for that period. 5 land cover classes were identified. So we have bare soil, mountain, which is effectively kind of rocky bare soil, quarries, urban, and vegetation areas. And you can see how this is represented in the sequential maps. In the lower right, you can also see that it produces a chart showing how the proportion of the different classes changes over the period of analysis. In this case, we can see that things actually have remained relatively stable, with the largest class consistently detected being bare soil. Unsurprising, since outside the river valley, this is a rocky desert area, and there's not any substantial increase or decrease in any particular class during this period. But basically, so this gives us our first broad overview of the study area, in that if there had been a huge sudden increase in 1 or more classes, for example, say a sudden increase in the amount of built urban areas, then this is obviously something we'd want to investigate further. To start looking at specific instances of change, users can then select 2 specific images that they want to compare. So in this case, on the top row, you can see we've just selected the earliest and the latest images for our period. And you can see the land use classification map generated for each of those images. In the bottom row, then we can see how the detected change has been mapped and displayed in different ways. On the bottom left, we can see a result which is similar to the one that we get in our original script. That is, it's just a simple binary telling us whether the script has detected any change in class for each pixel in red or no change in black. But on the bottom right, this is where we're able to start understanding the type of change which has occurred. Because what it then does is that it takes each type of change that is detected, that is where any class has changed to any different class and gives it its own classification. So I will try to explain this a bit better. So if we zoom in on a couple of sites, we can see in the upper left, we have two kind of late Roman or medieval village sites with a 100-meter buffer zone drawn around each of them. On the bottom left is the change classification image that I just mentioned. And I'm aware that it kind of looks like someone vomited confetti everywhere. But what it's showing is each instance where the pixel has changed its class from one class to another or remained the same. So from 5 initial classes, we get 25 change classes. So from bare soil to vegetation, bare soil to urban, or from vegetation to urban, and so on. Or the most common class, that is remained bare soil, that is no change has occurred. If we have a look at the charts on the right, we can see that the first one on the top gives a quick overview of the most common threat or classification change observed on the sites in the study area. So for each site, it takes all the pixels found within the buffer zone and calculates the mode, that is the most commonly identified change class within each buffer zone. So, within one of these circles, what is the most commonly found pixel? And we can see that by far, the dominant class identified was remained bare. So that is the largest change classification identified at most sites was in fact one of no change. So this sounds like good news, but however, this does not really give us the detailed picture. When dealing with Sentinel-2 imagery, we have to remember that even 1 or 2 pixels at 10-meter resolution could represent the construction of a new building and the destruction of an archaeological site. So the second chart shows the number of sites that have at least 1 pixel belonging to each category of change. So for example, if we just look at this one bar here, we can see that in this case, 165 sites, there are 165 sites where the script has detected at least 1 pixel within the buffer zone that had changed from bare soil to urban building. And so you can see it's done this for each of the change classes. And so this gives us a really specific look at the results of the distribution of sites and what are the kind of most commonly, or kind of what change most commonly affects most sites. We can also focus on information about just one specific classification and change classes that we're interested in. So for example, as we know that urbanization is a major threat to the archaeological sites of Beni Walid, we can also extract just those pixels that have to do with the urban classes. The first map on the upper left shows areas that remained urban between January 2019 and January 2023. So there has been no change. But then in the second map, we have all the areas that both either remained as urban areas or changed to urban areas from another class, basically showing us urbanization. Of course, as a caveat, this result especially depends on the accuracy of our classification. As I did mention, we are still working on full validation. And this is obviously really time consuming to check high resolution imagery for every site individually and confirm the results, but ultimately we will be able to report on the accuracy of the classification and our results. On the third map, we have a site that where we can see the construction of 2 new buildings. The archived images on the lower left, you can see shows that this site was bare soil in 2013, and you can just make out where the site number is. There's a couple of buildings here. I'm not sure if you can quite see them. But then in 2016, the construction work starts, carving out this terrace right into the side of the hill, and the ancient buildings are destroyed. And then we can see ultimately the construction of these new buildings. And you can just see them obviously highlighted here in the red. Finally, we can also start analyzing the data for individual sites where we can output the breakdown of the proportions of each change class identified within an individual buffer zone. So here, for example, we can see that for the most part at this site, the pixels that were already bare soil remained so. So you can see that here with 58 pixels. And similarly, pixels that were already urban, we have 59. That is existing buildings also remain so. But we can also see that we do have instances where the class called mountain which again is just kind of rocky bare soil, has changed to urban. Where is that? Mountain to urban. So there were 36 pixels that changed. So we can see, for example, if you look up kind of in this area here, we can see that there's been the construction of a new structure up here, an extension of this kind of modern farm. We can also see that there has been an area, helpful red arrows this time, where a great deal of vegetation has suddenly occurred. So you can see here it's kind of bare soil, but then in 2022, we have all these trees that have appeared. And you can see that this is picked up specifically by this kind of blue color here in the change detection classes. So changing from bare soil to vegetation. So also, finally, another thing that we can do, we look at the same site again, we can also go about this in a different way and detect change for a particular point in space over a period of time. So in this case, we may want to know exactly when in that period between January 2019 and January 2023 that this vegetation starts to appear. So when does this start to become a problem? So hopefully you can see the point P, it's a little bit small, but it's just here, which is just outside, it's within the archaeological site, just outside of the modern building's boundaries. Now we start our analysis in January 2019, and as we start moving through the archived satellite images, we can see that in June 2020, sorry, that's this one, we can see that they are starting to, the agricultural activity you can see kind of on the eastern side of this enclosure is already starting. And then if we move forward further in time, by September 2021, you can see that the vegetation has actually spread beyond the boundaries of the settlement into the archaeological site. Now, this is probably unintentional. It's probably due to runoff from the irrigation being used to help these trees grow, is running down the hill into the archaeological site, but then which is encouraging more vegetation to grow. And basically, this sudden appearance of vegetation is almost certainly going to have a detrimental effect on the integrity of the site. Now, on the bottom left, you can see the outputs for this particular pixel and how the algorithm has determined that a change has occurred. Sorry, just scrolling through the rest of those pictures. And so you can see clearly in the chart in the upper right then, the exact point in time when the change in classification from bare soil to vegetation occurred. And that is shortly after January 2021. And you can see we're going along nicely as bare soil, and then all of a sudden it jumps to vegetation. This vegetation growth is also incidentally corroborated in the increase of the NDVI values for this point, shown in the bottom right. Basically what I hope this shows is how this kind of method gives us a variety of different types of outputs and ways that we can visualize and analyze changes that have occurred in the vicinity of archaeological sites and the landscapes around them. So now I just want to quickly have a look at our second case study over in Morocco, much more briefly. Now here again, we have the study area outlined in red with the distribution of sites in blue. This area, the Bunu Plain along the Wadi Dra in southern Morocco is home to a series of abandoned medieval oasis settlements, as well as prehistoric cairn cemeteries. In this region, sites are increasingly under threat from processes like shifting sand dunes and flash floods. These are, of course, all natural phenomenon, and they've been happening for thousands of years. But the problem is that they are increasing in speed and severity and being generally exacerbated by climate change. So if we have a look at the site on the right-hand side, this is an early modern house where I helped direct some excavations this past November. And you can see in the background the sand dune, which is literally moving right over the top of this house. So here again on the left, we can see our time series of the change classification maps. And the main thing you can see is how significantly the bare soil and the sand dune classes, so those are the two kind of the light and dark beige classes, how they shift around and change quite significantly. We can track this at a specific point within the house structure that I just showed. And we can see in the satellite image in the upper right at point P. So then if we look again at the time series classification for this point in the bottom right, in this case, we can see that the classification was identified primarily as sand dune, though for a brief period it was bare soil, and then back to sand dune. And so this is actually the threat in itself. It's the movement of the dunes over the top of the site, back and forth, continuously eroding it, which is the problem here. In this particular case, we're hoping that we can do some more in-depth studies about the movement of sand dunes in this region and the effect that they're having on archaeological sites in the area. And what this gives us is a really useful starting point to be able to track the frequency and timing of movement over the tops of these sites. So this is still very much a work in progress, as I've said. And as I mentioned a couple of times, we are still working on validating the results. And along the way, we have, of course, encountered some challenges. Something that is always an issue when you're training classification models is misclassification. One frequent problem is with shadows that we have found, and we're still looking kind of for the best practice for dealing with this issue. Another issue that seems to be particular to the desert regions where we are doing our work is that there is a high level of misclassification between classes such as bare rock, sand, and even some built up areas, because many rural settlements in this region are constructed of earthen materials like mud brick. So you can see in the image in the upper left, for example, how the buildings constructed of modern materials stand out, obviously, much more than those which are clearly built of earthen materials. They're still obvious to the eye when you're doing kind of a visual interpretation, but the machine learning definitely is having some trouble differentiating them at lower resolutions. So this is definitely something that we are still trying to figure out what is the best way to deal with this problem. And in fact, any suggested solutions from the audience during question times would be welcome. Now also, while near the beginning of my talk, I obviously spoke about the great advantages of Google Earth Engine and why we use it, but we are also starting to hit some limitations with it. One problem at the moment is that there are limits of the memory available in Earth Engine, which makes doing very heavy analyses and an issue. We're also kind of investigating workarounds for particular issues, for example, like importing the training samples using different methods, but it does limit what we're able to do with this platform. Now, another really important thing that we have to take into account with Google Earth Engine, and also potentially limits its use by our partners, is the fact that it requires people to use the code interface, which you can see on the screen. I mentioned at the start that one of the most important things that we do is not only the development of these tools, but also making sure that these developments are being shared with and are accessible to our partners in the Middle East and North Africa. Now, most archaeologists in the region, and I'd say worldwide, including myself, not actually trained in how to do coding or kind of these advanced remote sensing techniques. I certainly never imagined when I started my career in archaeology that this is the kind of thing that I would be doing. Though I do think this is starting to change with newer generations of students and as more digital methods become embedded in the discipline. But the issue is that we found when teaching other heritage professionals how to use Google Earth Engine, there are some who happily pick it up, but there are still others who sometimes have lower computer literacy and can find working with the code sometimes confusing or kind of intimidating. So while we are training people, obviously, how to use Google Earth Engine directly, a really important thing that we're working on alongside the main development is producing free online apps, which are going to allow people to bypass the code altogether like this. So what you would see is something like this instead, where you're able to simply enter your basic parameters for your analysis into the form that you can see on the right-hand side, in what I hope is a really straightforward way and accessible for any level of user. Now, the version that you can see on the screen makes available our initial binary change classification system. So it's the simpler system. And we hope to have that online and available for people to use very soon, actually. But then we also do want to make user-friendly versions of the more complex detection scripts as well. Another route that we're looking at is the development of a QGIS plugin, and which would in theory also link to the EMENA database to create kind of a direct monitoring system for the sites within the database without having to go through the process of exporting and things, so that it would be kind of a one-click operation. Finally, another consideration that we're starting to think about is how we make these tools that we're developing sustainable in the long term, so that they can hopefully be used by our colleagues in the Middle East and North Africa and elsewhere long after our project has probably ended. Google Earth Engine is obviously, as I've said, a really amazing tool, but while it's currently open access, there's no guarantee that it's going to remain that way forever. So we're also looking into alternative platforms like Jupyter Notebook, and whether we want to invest into developing our own bespoke platforms. But this is a conversation that we are only just starting to have. And so that's everything. Thank you very much for your attention.
Thank you very much indeed. That was absolutely fascinating, and the amount of data you're processing is completely overwhelming. I thought I had a lot to do. That's just next level. So we've had some questions online. I was busy preparing some questions, but I don't think there's going to be any shortage. So first, I'd like to just ask one of the questions that's appeared on the YouTube chat, and then perhaps we'll open it up to the room. So our first question is from Pamela Achungo, and I hope I've pronounced that correctly. What accuracies were you able to achieve with regard to classes that are spectrally similar, for example, grassland and shrubs? And I think you may have already just touched on that.
Yes, so I'm afraid, I am very sorry that I can't answer that question yet, because yes, but that is obviously something very, very important, and it's a very, very good question to ask. Basically, I am still currently in the process of going through the validation. Between those two case studies, there are about 600 sites. So as you can imagine, having to go through and do the visual inspection of the high resolution imagery and then comparing them each individually to the results that the ACD has given us is taking a little bit of time. So I'm not quite there yet, but I promise we will have that information, and hopefully we'll be publishing a paper about this over the summer, about this method, in which will obviously include the accuracy information as well.
Fantastic, thank you. So I have another question from YouTube, but first of all, I'd like to open up to the floor. Does anyone have a question they'd like to pose to Nichole? Emilio.
Yeah, I have a question about coding. So when you,
I wish Ahmed was here.
when you show that in a certain point you can track the changes in classification, does exist any way to see if a pixel has experimented any changes, regardless of the initial and end point? And I explain this. So, for example, if you have an area that has gone from bare soil to urban into bare soil again, is there any way to have a coverage of the area that marks, okay, this pixel has experimented a change during this time series?
Yes, yeah. I think sorry, that is, I think, what the so for example.
Yeah. So something like that, but
yes.
For the whole area.
Oh, for the whole area. I'm not completely sure. I'll have to find that out for you. I mean, basically, that's what obviously the map is showing, the individual changes of each image. But no, I'm not sure there's a way to show that in chart format. That's why we use the kind of visualization methods of using the different kind of the different colors seen here. But again, I guess, yeah, you're right. That is still a comparison between two images. Yeah. Yes, I would have to think about that is the answer, and talk to Ahmed about that. I'm not completely sure how you would visualize showing that for an entire area. Yeah.
Thanks, Emilio. I'll jump in with our other question from YouTube. So this is from Ivan Innocent, and he asks, I noticed a number of Maxar satellite images in the slides. Can I access high-resolution Maxar images from using the Google Earth Engine API, especially if I want to use them for validation?
Short answer is no. So all of the high res, so like on the images that you see on this slide, this is from Google Earth, from Google Earth Pro. Now within the Google Earth Engine interface, so I'll just show you the interface here. So this is also like this is Maxar. Oh no, Terra metrics. Anyway, this is high resolution imagery that you can use in the interface, but you can't use this imagery for your analyses in Google Earth Engine at the moment, because yeah, that imagery is not free for that. As I mentioned, we are looking for ways that we can do that. So if you have high resolution imagery, if you actually have the image files, I believe it is possible to upload them to Google Earth Engine, and then you can run the analyses over them when you've uploaded it, but you cannot access that data in a way that will let you run analyses over it in this manner from Google Earth Engine. That sounded really complicated, but yes, short answer was no, you can't.
That's great, thank you. Emilio, if you could keep an eye on the YouTube channel for chat, that would be great. Any questions from the floor, please? I have a question if there's no one else. So I'm interested in you're monitoring all of this change, but what actually happens if there is significant negative change on the ground? I realize it's a vast area that you're covering, but could you give an example of an outcome of that change being identified?
Yes. So, I mean, we are still like in these case studies, for example, obviously from our end, we would want to then look for ways to validate it. So what we would normally do is we do have colleagues in Libya who work in the DOA there. And what we would ideally want to do in this case, for example, with the Beni Ulid case study, is to provide them with a list. So we would run our ACD, identify the sites where we've done the analysis, we've done the validation using high resolution imagery to check which sites have the most threat. And ideally, we would basically give them this list of the sites where change has been identified and ask them to go out into the field if they're able to validate this on the ground. But then ultimately, it would be kind of up to the DOA to take this forward. We are also later this year, we'll be running training events like the ones I mentioned at the beginning of my talk. And so we'll be doing more to also teach them how to do this themselves, because obviously we're not going to be able to do this forever. Our project does not go on forever. We have limited funding. And yeah, that's really ultimately what we want to do, is we want to train them how to do it from start to finish. But for now, yes, we are kind of doing the analysis, but then passing on that information to the relevant authorities. And yeah, but there's only so much that we can give them information, but it's sort of up to the people in those countries, because it's their, it is their responsibility, it's their heritage for them to decide what they're going to do with that information.
Fantastic, thank you very much. A final check on our chat. Any questions again? In that case, I think we'll close today's seminar, and thank you ever so much for attending. Thank you also to our online audience, of which there have been quite a few people listening, and so that's fantastic news. A reminder to join us for our final seminar of the 2022-23 series in June, and a huge thanks again to Nichole and also to Ahmed in his absence. Thank you very much.